So, this isn't how I thought I'd be starting this week. I tested positive for COVID. Nobody else in my house has tested positive, so I'm stuck in my room. And so, while I'm sitting around doing nothing, I thought I would go ahead and try to get some lectures put together for you guys so you guys can continue the content even when I'm out. I hope to be back just as soon as possible. So I always like to start the week schedule or the week with the week schedule. This is obviously going to be a little bit different now. I would change this, but this is saved on my desktop at school, what I can't get to. But so the main thing that I want to talk to you about the week schedule, it's obviously going to change. I think I'm going to keep our all gas laws quiz still on Friday. So we're going to learn a little bit about gas laws and quantifying what we learned on last Friday. So we're still going to shoot for a quiz on Friday. And then the biggest thing is about tie-dye. Because Mr. Pilcher is going to tie-dye the day after me, and he was going to tie-dye the 12th if we were going to tie-dye on the 11th. That 12th, I believe, is the AP World Test or something. But anyways, it's one of the AP tests that takes out a ton of our students. So we're actually going to move tie-dye up one day. We are now going to tie-dye next Tuesday, which will be May 10th. So still want to bring that 100% cotton t-shirt in whatever size you would like and whatever cut you would like. And then one roll of paper towels. Doesn't have to be the nicest roll of paper towels. We just need that to keep the dye from spreading. And so that means next Monday we'll talk all about how to tie-dye. Make sure you guys are all ready. And then we will actually dye on Tuesday. So, like I said, the rest of all this is going to get all kinds of messed up, and I don't know what day I can come back. But we are going to keep on trucking here. So if you are in my third period class, go ahead and get out your note packets. If you are not, you should be given these notes here, Unit 9, gas laws, Charles and Boyles law. I thought it was just easiest, especially because I'm not there and I can't interact with you guys if I just gave out these notes this way. And then we can just have everybody get exactly the same information. I feel bad because this is a pretty interactive lecture. So I'll be talking to myself, but that's, it's all right. So wherever you have these, you do need a calculator for today. The laws start off very simple and then they get a little bit more complex. So what we're going to talk about first is Boyles and Charles law are basically laws that describe gas behavior. Okay. Ooh, well, and I found this mouse in my basement and it has a mind of its own. Okay. Let's try that again. Boyles and Charles law are laws that describe gas behavior. That 3 really just wanted to come up there. And when we talk about gases like we did on Friday, we talked a lot about how kind of the mechanisms behind volume, pressure, and temperature. And we did the PhET simulator where we got to see the molecules moving and everything. So now we're going to talk about if you had to put these different variables into numbers, what you would see. So volume is always going to be measured in liters. And you got to be careful of milliliters. And remember, we've already done this liters to milliliters business when we were doing molarity. And you always want to move your decimal 3 times to the left. That might be the right to you. Is it backwards? I don't know. Okay, moving on. You want to move the decimal 3 times to the left. Then pressure is always measured in atmospheres, and the short way to write atmospheres is going to be ATM. There's lots of different ways to measure pressure, like PSI and things like that. But when we're talking gas laws, the most normal or most widely used pressure measurement is going to be atmospheres, especially for us. Just to give you a frame of reference, sea level is 1 atmosphere of pressure. So here in Ohio, we are actually a little less pressure because we're a little bit higher than sea level. Temperature is something that we're also going to need to talk about when we talk about gases because it can drastically affect volume and pressure. And we're going to use a different type of unit for temperature, and we are going to use Kelvin, which is K. And I could spend a lot of time going on and on about why we use Kelvin and absolute zero and about how the molecules slow down all the way until they don't move anymore at absolute zero. We haven't really gotten to that yet, but I'm sure you don't want to hear me drone on about that over a video. So we're going to use what's called Kelvin. And often we don't have thermometers that read Kelvin. So you're going to have to take your Celsius and convert that into Kelvin. And so what you're going to do is you're going to take your degrees Celsius and you are going to add 273. So absolute zero is zero. And then, like freezing on the Celsius scale, zero would be 273 degrees Kelvin. So the 1 and the 2 you're going to see on these formulas. 1 means initial and 2 means final. You might see them written in the future as like P instead of P1, it could be PI for initial and final. It depends on how some people like to write it, but I use 1 and 2 because that's what's commonly used, and that's what our AP Chem teacher uses as well. So with that said, hopefully everybody's feeling good with our variables. So let's go ahead and get into the actual laws themselves. So like I said, I got some videos and stuff that I would be playing if I was there. I'm going to try to play them here, but it's hard to talk to you when I'm not there. But so if you were to go to the bottom of a pool and you were to blow a bubble, okay, what would happen to the size of that bubble as it rises up to the top? And I probably gave it away by not erasing this, but hopefully here, let's just show you the video instead. What would happen to the bubble if you blew it down the bottom of a pool and then as it rises to the top? Let's see. Wonderful. We'll do one that we can see. Boop. All right. So you can see this bubble. Okay, get to one that you watch all the way up. All right, so there we go. As you can see, as the bubble rises to the surface of the water, it gets bigger and bigger and bigger and bigger and bigger and bigger because the pressure on the outside of that bubble is subsiding. So when you really put the pressure on that bubble way down at the bottom of the water, it will make the volume quite small. And I found this one a few years ago that I thought was pretty cool because I don't know how he has so much air in his lungs. So we got a monofin here. He's swimming to the bottom. We can probably go a little faster. All right, here we go. So they're going to have a nice shot going over. So again, when the bubble is at the bottom of the water, it is small. And as it rises, there's a decrease in pressure pushing those gases together. And if there is a decrease in pressure, then that could be an increase in volume. And so he just got these bubble rings. But I like how you can see how they're smaller way down low. And then as they rise, there's no gas being added or removed. It's the same amount of gas that he blew out. But you can see that they get bigger and bigger and bigger as they go to the surface of the water. And then he like literally goes on forever. So awesome. So hopefully what you were going to say with my little picture is that the bubbles get bigger and bigger and bigger as they go to the top. And so we can actually quantify that. So Boyle's law talks about how the volume of a gas decreases as the external pressure increases. So if you increase external pressure, you can actually make the volume of a gas go smaller. And then obviously on the flip side, as the external pressure decreases, the volume increases. So as I let go on that external pressure, the volume then can get bigger. So again, the bubble rising in a pool, they get bigger as you reach the surface. So maybe you can sketch yourself a nice little fish. Oh, that's so bad. Woo. Fishes don't even blow bubbles now that I think about it. But in this little box, if you want to just talk about how as you decrease the pressure, so at the very bottom, there's lots and lots of pressure. So pressure is high. And then as it goes up, the pressure is lower. Okay, this mouse does not work. And then the volume will get bigger. Okay, so here's a shortened way kind of to put it together. And remember, we're talking external pressure because I do know if you build up pressure inside, it's going to make it get bigger. But we're talking about external pressure here. So Boyle's law says that as pressure increases, volume decreases. And as pressure decreases, volume increases. So you can push gases together and you can release gases. And so if you needed to quantify this and do some calculations, okay, you would follow this equation. Boyle's law is P1, remember that's initial, times V1, also initial, is equal to P2 times V2. So the initial pressure times the initial volume is equal to the final pressure times the final volume. Okay. All right, good stuff. Let's talk about Charles' law. Charles doesn't have anything to do with pressure. What Charles wants to talk about is he talks about volume and temperature. So what happens to the volume of a gas when it is heated? Hopefully you guys kind of see what's going on here. As it's heated, the volume of the gas will expand. And remember, the gas particles themselves are not getting bigger, okay, but the gas is getting further away from each other. And if you were to then go the opposite way.
Ever wonder what happens to helium balloons at minus 40 degrees? Well, let's find out.
He's going to take the helium balloons out to minus 40 degrees. I don't know if you can hear that, but they were nice and inflated in the warm apartment or house. Wonderful. And then now you can see that the volume of the balloon is coming together. It is contracting. The balloon itself is looking all wrinkly because it's not as much volume of gas inside of those balloons. So let's talk about Charles' law. Charles' law is as the temperature of a gas increases. All right, what are we doing? We don't want that. As the temperature of a gas increases, the volume also increases. As the temperature decreases, the volume also decreases. And hopefully you know those. That kind of makes sense. You've notoriously been around gases your whole life, and so you kind of know what's going on there. And then a hot air balloon, the balloon is heated and the balloon itself expands and gets bigger. So whatever you want to say, do a little drawing here of hot air balloon. This is going to go really well, I can tell. So we have hot air balloon. Yep. And then we're going to add some fire. And then the hot air balloon is going to get bigger. Awesome. Let's just continue on, shall we? All right. So Charles' law says as the temperature goes up, the volume also goes up. And as the temperature goes down, the volume also goes down. So you know that they're going to be directly related. So the equation for this one is going to be that the vegetables are on the table. So V1 over T1, the veggies on the table, is equal to V2 over T2. So that's the initial volume divided by the initial temperature is equal to the final volume over the final temperature. And so what you're going to be doing is you're going to be given 3 out of the 4 variables, and then you have to solve for X. And the way that you would solve, if you needed to solve for one of these, is quite simple. All you have to do is cross multiply. Okay. All right. So that is the end of the notes. So hopefully if whoever is leading this class right now, if you could pause the program, and then if you could pass out the Charles and Boyles law worksheet number 1. Oh, I guess I could just show you on here. Beautiful. Worksheet number 1. All right, so with your calculators fired up, I also should say that you can write these on the back of your periodic table. There is a spot right after the stoichiometry, kind of in the middle, it talks about the gas laws. We're going to add more like STP and stuff like that a little bit later. But we do have room for these if you want to write them on your periodic table. I know you didn't need them to the periodic tables today, but you can always put that there as a reference. And then you can use that on your quiz on Friday to have the formulas. So Boyle's law, we just said, is P1V1 is equal to P2V2. The initial pressure multiplied by the initial volume is equal to the final pressure by the final volume. And then Charles' law is V1T1 over V2T2. We talked about how pressure is in atmospheres, which is ATM. Temperature is going to be in Kelvin. And if you get Celsius, all you have to do is add 273. And that's going to be one of the tricky things. You're going to want to just use Celsius as the temperature, and you can't just do that. And then volume needs to always be in liters. And then you move the decimal 3 times to the left in order to take it from milliliters to liters if you're going to put it into the equation. All right, so the first thing we want to do is we want to read through and figure out what we are working with. The temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my refrigerator this mouse has a mind of its own. The balloon in my refrigerator that initially has a temperature of 22 degrees Celsius and a volume of a half a liter, what will be the volume of the balloon when it's fully cooled by my refrigerator? And so the idea here is that it's not always in order. Sometimes people look at, oh, there's 4 degrees, so that's my initial temperature, and then 22 must be my final temperature. And you have to kind of be able to read these real world scenarios to know kind of how this will happen. So let's first pick which of our laws we're going to use here. And you can see that we have temperature and we have volume. So I know if I have temperature and volume, I'm going to use Charles' law. Excuse me. I'm going to use Charles' law. And I'm going to write that here, not because you would have to write it on the quiz, but just so you know what I'm looking at and what I'm using. And that's V1T1 over V2T2. So I go through and I see that, okay, I have my refrigerator at 4 degrees Celsius. Before I even go any further, I don't like that number 4 degrees Celsius. Nay, nay, I do not. So what I'm going to do is I'm going to take that number 4 degrees and I'm going to add 273. So when you do that, I'm not even going to pretend to write that on here, but when we get there, we're going to add that. My mouse would be a little bit better here. We would do 277 degrees for that one. Then it says my balloon initially has a temperature of 22 degrees and half a liter. So those are going to be my first two variables. Okay, maybe it's better if I just use the touchpad up here, even though it's like a little slower. So what I'm going to do is I'm going to take my 22 degrees here, and I'm going to add 273. And so what my initial temperature is going to be is it's going to be 295 degrees Kelvin. And my initial volume is a half a liter. So hopefully you understand because it says initially like that. Then I'm going to put that balloon into a refrigerator. Now, sometimes before I get going, I want to think about it. I have something at 22 degrees. And then I'm going to take that gas, I'm going to put it into a refrigerator that's 4 degrees. If it was a half a liter, do you think when it's done, it should get bigger if the temperature drops? Or do you think it should get cooler? I mean, smaller if the temperature drops? So as we get going here, just think about what number. Should it be bigger or smaller than a half a liter? Because a lot of these will make sense for the answer. And if they don't, you know you did something wrong. So my final volume is the question. What will be the final volume? If I cool it down to, and again, I'm not using 4 degrees, I'm going to use 277 degrees. Now, what we're going to do to solve for this is we're going to cross multiply. Boop. So we're going to do 295 times V, which is going to give us 295V, or X. And then I'm going to do 0.5 times 227, which is going to get me 138.5. And then hopefully you know algebraically how you solve for this is we're going to divide both sides. This is going to be fun to write, by whatever number is stuck to X. So I'm going to divide both sides by 2, 9, 5. And then that would get X by itself. And if in your calculator you did 138.5 divided by 295, the number you would get, let's see if we can find it here, is 0.47. Now we need a unit. So it was volume. And so looking up at the top, or just maybe you know, volume is in what unit? Good. It is in liters. So let's go to the next one. Oh, heavens to Betsy Lou. Where did that go? I meant to go down, not over. All right. Synthetic diamonds can be manufactured at pressures of 60,000 atmospheres. If we took a 2 liter of gas, like a 2 liter bottle, at 1 atmosphere, which is sea level, and we compressed it to the pressure to make a diamond, what would the volume of the gas be? So first of all, if you took a 2 liter of gas and you put it under the pressure it took to make a diamond, do you think it's going to get bigger or do you think it's going to get smaller? And if you think it's going to get smaller, do you think it's going to be way, 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 way smaller? And the answer to that is way, way, way smaller. So let's see. When I see pressure and volume, I know that I'm going to be using Boyles law. Okay, this one right here. So I'm going to move that down. Boyles law. And that's P1V1 equals P2V2. Now, this one isn't really kind of very tricky. There is no temperature in this one. So synthetic diamonds can be manufactured at pressures of 60,000 atmospheres. If we took a 2 liter of gas at 1 atmosphere, so those are my initial numbers. So I'm going to take, whoopsies, where am I going to go here? 2 liter at 1 atmosphere, and I'm going to compress it to 60,000 atmospheres, like the pressure to make a diamond. What would be the volume of it? So obviously we're going to crush it. It needs to be a very small number. So I'm going to actually, a lot of people will just do the math wrong because it feels weird to divide here, but I'm actually going to take 2 divided by the 60. Lots of zeros in this number. Let's try the mouse again. Okay. No. 2 divided by 60,000. That didn't work either. Cool. I'll be glad to be back with my smart board soon. And so if I do actually 2 divided by 60,000, you're getting a tiny number. Depending on your calculator, you might get some scientific notation. But the volume is going to go from a 2 liter to 0.00000. Did I say enough of those? 3. And again, if it's volume, what's the temperature going to be? Or what's the unit going to be? It's going to be liters. So what I want you to do is just go through these, go ahead and answer these. You should be getting an answer key. I don't know if it's orange or not. I'll have to thank Mr. Pilcher for making copies of the key and putting them out for me since I am not allowed in the building. But so I'll just start this next one for you so you can get going here. On a hot day, you may have noticed that a bag of potato chips seems to inflate, even though they have not been opened. If I have a 250 milliliter bag. So remember, moving that decimal 3 times to the left. 250 milliliters is actually, we're going to type that. 250 milliliters is actually 0.25 liters. So make sure you use that in your equation. And the temperature was 19 degrees Celsius. Don't like that either. You better go ahead and turn that, add 273 to that. And then I leave it into my car, which has a temperature of 60 degrees. What will be the new volume? So hopefully you know here that you're doing temperature and volume. So that's going to be Charles' law, V1 over T1 equals V2 over T2. And then make sure that you change both of your numbers into Kelvin before you put it in there. But think about it. If it's a room temperature bag and then you heat it up, what should happen to the volume of that bag? Should the bag get bigger or smaller if you heat it up? So I'll just stop rambling. I don't know why I'm just still talking, but I hope you guys have a great day. I probably won't be in tomorrow, so I will have to make another one of these videos tomorrow for you. And we'll go on to the combined gas law. And hopefully I'll be back on Wednesday. If not, Thursday we'll hit the ground running for sure. And we have a quiz on all these gas laws on Friday. If you need anything, please email me. I will be locked in my room. But so I hope you guys have a good day, and I will talk to you guys soon.